Let's look at the ocean part of this buoyancy, or creation of buoyancy. So in the ocean, as we said, it's an incompressible fluid for all practical purposes, so we can go back to density instead of worrying about temperature and jumping between pressure and temperature and so on as we do in the atmosphere. You can write buoyancy like before we said, reduced gravity, so g times rho 0 minus rho over rho 0. So if you perturb the water parcel by a little bit compared to the background density, then what happens? We already said the density of the ocean water can be written as a function of temperature and salinity. We can linearize it for small perturbations around the thermal contribution and the salinity contribution. Obviously, this is inconsistent with the statement that it's a very nonlinear function, but for small perturbations, it's okay. So as we increase the temperature, we want the density to decrease, and if we increase the salinity, then density should increase. So this formulation takes care of that. The total heat flux at the ocean surface is given by this, where again it's the net radiative forcing, short wave minus long wave. Sensible heat, this term of sensible heat added by precipitation is generally a small term, but Peter Webster likes this term. In general, we don't write about it. And then there is the latent heat flux. There is also a part where the radiation penetrates below the surface, and that has to be taken care of in most cases, and that depends on the amount of pollutants or chlorophyll and other things that are there in the water, organic matter, etc., which can trap the radiation, etc. So we may get into those details later on. So here the net radiation forcing is of course incident solar minus outgoing long wave. So here we are looking at the mean sea surface temperature and columnar integrated heating. We have the ITCZ and the distribution of rainfall clearly seen, and sea surface temperatures are warm where there is a lot of rain, and it's cold in the upwelling regions like the East Pacific, very obvious, the Somali coast here, and high latitudes of course have colder temperatures below 20 degrees centigrade. We are mostly focused on the tropics, so we can think of it as approximately 30 south, 30 north, which is captured by this. These contours are heat fluxes, and the contours go from 20 to 300 watts per meter squared. The convention is always done differently in different books or by different people. The integrated heating in each SST level here is 25, 48, and 27% of the total heating that occurs between those sea surface temperature bands, 27 to 28, 28 to 29, and 29 to 30 degrees centigrade contours. This is averaged over the period of 1971 to 2001. So the column integrated heating distribution here is derived from the ECMWF era 40 reanalysis. Remember what we said before? Reanalysis is a merger of data and models with certain protocols of errors in the data, errors in the models, and how they are merged, which method is used, etc., can make a little difference. People have also analyzed the problems with reanalysis in terms of dynamic consistencies, with observations, etc. But nonetheless, they are mostly used as reality. Okay. What else can I say about this? If we look at columnar integrated heating, we can see here the bands shown, 22, 21, 22, 23, and so on. This is watts per meter squared. They're negative in here, and it's positive over here. The convention has to be carefully considered, as I said before. For example, here negative means going into the ocean, okay, and positive means coming out of the ocean, okay, even though it's a columnar heating that we are talking about. The convention is important. The other way to think of it dynamically is that where the ocean upwells and brings cold water, the atmosphere heats the ocean, and where the ocean tends to be warm, there is a loss of energy from the ocean into the atmosphere. So, for example, the western boundary currents that we talked about bring warm tropical waters into these latitudes where the atmosphere is very cold. Similarly here in the Gulf Stream, and you can see that the ocean is losing lots of heat here. Similarly, upwelling here is forcing the atmosphere to try to heat the ocean. So you have to be careful about those sorts of things. Okay. Looking at freshwater flux going into the ocean, it's written as evaporation minus precipitation averaged over the globe and over time. So you can think of buoyancy flux as the heat flux plus the freshwater flux. For example, if you put heavy salt water, it's going to make the water sink, which is what the deep water formation process is, where evaporation can remove energy and leave salt behind and create heavy water, or in the Southern Ocean where brine release and so on from the ice shelves, etc., can create heavier waters. This is written filling in for the heat flux as G alpha thermal divided by rho CW. Obviously, the heat flux is going to affect the temperature, and freshwater flux is going to affect the salt. So we have split those terms this way. This is our net heat flux, and this is our net freshwater flux. Just for consistency, we have switched the sign here from E minus P to P minus E. So you just have to make sure that the sign of the freshwater flux corresponds to the density change. So if you increase precipitation, you're going to make it lighter because fresher water, so it's going to increase buoyancy, right? The idea is that when rainfall temperature is measured, it tends to be slightly colder than the ocean, I think. So that's how the sensible heat of the rainfall into the water is accounted for. This is now looking at annual net ocean atmosphere heat flux in watts per meter squared as a map. As I said, there are coastal upwellings here. There is equatorial upwelling here. So you can see the Gulf Stream and the Kuroshio are bringing warm tropical waters, as well as here in the southern hemisphere boundary currents, the East Australian current and the Brazil current. It's also called Brazil Malvinas current, I think. So in general, you can see that wherever ocean is dynamically lifting cold water to the surface, atmosphere tries to damp that cooling, which means ocean is taking up the heat. That's important to remember, because when, for example, we will see El Nino reduces upwelling, that means the cold water coming up is not as cold, or the warming is needed to damp the ocean cooling is dynamic cooling is not as strong, so the heat flux reduces, whereas on this side warm temperatures are going to get colder and take up more heat from the atmosphere. Okay. Indian Ocean, of course, because of the monsoonal circulation, is always different. This is looking at annual net freshwater flux E minus P going into the ocean in terms of millimeter per day. So you can see that E minus P is negative in the ITCZ, in the warm pool maritime continent region and the monsoon region, broadly everywhere, and the evaporative latitudes of the subtropical gyres are clearly seen as positive E minus P regions, where evaporation is always higher than the precipitation. So here salt is left behind and water is made heavier. It's also converging because the subtropical gyres are converging regions. Here there is upwelling, and you can see that the ocean is taking up heat, but there is no rain, so it is a minimal E minus P positive region here. So consistencies are there, which is what we always look for as well, because there will always be errors in the fluxes, because fluxes are not usually measured directly. You cannot measure directly latent heat flux and sensible heat flux. Long wave you can measure, short wave you can measure. As we saw before, bulk formulae are used for deriving sensible and latent heat fluxes. So you are measuring temperature and humidity and then computing the fluxes. So already there is propagation of uncertainties and errors, for example. So looking at buoyancy flux in terms of meter squared per second cube as with a factor of 10 to the minus 8, where there is positive buoyancy, that means you are losing buoyancy. So you are going to let's make sure. Buoyancy flux from heating, buoyancy flux from fresh water, and warm colors show an increase in buoyancy, while cold colors denote a loss of buoyancy. So here heat loss means ocean is getting colder, it's losing heat to the atmosphere. Here ocean is gaining heat, so it's gaining buoyancy. Surface waters are getting warmer because of the heating, and the buoyancy flux, this is the total. This is from heat flux and this is from freshwater flux. As we can imagine, the flux from freshwater flux is higher under the ITCZ and the subtropical gyres with opposite signs. ITCZ is putting more freshwater and producing positive buoyancy, whereas the evaporative losses in the subtropical gyres are leaving salt behind and taking out buoyancy or making the waters heavier. That's the way you can think about it. This is the same as the previous figure, but here we are averaging over DJF and JJA, and you can just see the hemispheric shifts in the total buoyancy flux, right? The winter hemisphere is losing buoyancy and the summer hemisphere is gaining buoyancy, except these deep tropical regions where upwelling is creating buoyancy basically throughout the year. You can see JJA has positive buoyancy here, and also DJF. So otherwise hemispheric shifts happen in the ocean buoyancy production and loss. We'll come back to this in terms of observations. There have been observational programs which have measured various quantities of ocean parameters, atmosphere parameter, convection, ocean atmosphere interactions, and so on, which will nicely tie together all these various buoyancy and freshwater fluxes and heat fluxes that we have been looking at so far.